Have you ever wondered how we ensure the safety and quality of our pharmaceutical products from harmful microbes? Welcome to the fascinating world of microbial limit tests, a critical component in the pharmaceutical industry. Think of it as a gatekeeper, standing guard to ensure that no unwanted microbes are hitching a ride on your medication. Microbial limit tests are a two-pronged approach. First up, we have viable count. This is our head count of living microorganisms in a sample. It's like taking attendance, but instead of students, we're counting bacteria and fungi. Next, we dive into the identification of specific microorganisms as per IP. This is where we look for particular troublemakers, the kind of microbes that could pose a significant threat to human health. Together, these tests safeguard the purity of our medications, providing a crucial line of defense. After all, who wants to ingest a pill teeming with bacteria? Now, what exactly does a viable count mean in this context? Imagine a bustling city, full of people going about their daily lives. Now, what if you wanted to know exactly how many people were active in that city at a given moment? That's a bit like what a viable count does, but instead of people in a city, we're counting live microorganisms in a sample. The viable count, also known as the plate count or colony-forming unit count, is a method used to estimate the number of living microorganisms in a sample. It's not about counting every single microorganism, but rather just those that are alive and capable of multiplying under favorable conditions. So, how is it done? The process involves diluting the sample and spreading it over the surface of a solid medium. This medium provides the right conditions for the microorganisms to grow and multiply. After a specific incubation period, the colonies formed are counted. Each colony is assumed to originate from one viable microorganism in the sample. Hence, the number of colonies gives us an estimate of the viable microorganisms present in the original sample. Now, you may be wondering, why is this so important? Well, in the world of pharmaceuticals, safety is paramount. Microorganisms can be harmful, and their presence in pharmaceutical products can lead to infections and diseases. By conducting a viable count test, manufacturers can ensure that their products meet safety standards and are free from harmful levels of microorganisms. But remember, a viable count is not a definitive measure of all the microorganisms in a sample. It only gives us an estimate of the live ones. There may be others that are dormant or non-viable and thus won't show up in the count. So, a viable count is a bit like taking attendance of the microorganisms present. It's a simple yet crucial tool in maintaining the safety and integrity of pharmaceutical products. But how about when we need to pinpoint a specific culprit amongst these microbes? You might wonder. Well, that's where the process of identifying specific microorganisms comes into play, as outlined in the Indian Pharmacopoeia, commonly referred to as IP. This process is akin to a detective scouring a crime scene for clues, but instead of looking for fingerprints or DNA, we're searching for unique characteristics that can help us identify our microbial suspects. These characteristics can be anything from the shape and size of the microbe to its preferred environment and nutritional needs. The IP provides a standard method for this identification process. It's like a rulebook that ensures consistency and accuracy in our microbial investigations. This process starts with isolating the microbe from the sample. It's like plucking a single strand of hair from a crowded room. This isolation allows us to study the microbe more closely without any interference from other microbes. Once we have our isolated microbe, we can start the identification process. This involves a series of tests, each designed to reveal more about our microbe. These tests might look at how the microbe reacts to certain chemicals or temperatures, what kind of food it prefers, or even what color it turns a specific test medium. This information is then compared to a database of known microbes. Think of it as a lineup in a police station, but for microbes. By matching our microbe's characteristics with those in the database, we can identify it with a high degree of certainty. This identification process plays a crucial role in ensuring the safety of pharmaceutical products. By identifying potentially harmful microbes, we can take steps to eliminate them, ensuring the product's safety and efficacy. As you can see, identifying specific microorganisms is like finding a needle in a haystack. but with the right techniques, it's possible. And not just possible, but essential in the world of pharmaceuticals. So next time you pop a pill or apply a cream, remember the detective work that went into ensuring its safety. So, how do these tests work in reality, you might ask? Well, let's dive right into the fascinating world of microbial limit tests. The process begins with sample preparation. This is a critical phase as the accuracy of the results largely depends on how well the sample is prepared. It involves homogenizing the sample to ensure a uniform distribution of microorganisms. Depending on the type of product being tested, different methods of homogenization might be employed. Once the sample is ready, it's time for the actual tests. The viable count test, for instance, involves spreading the prepared sample across a growth medium. This medium provides the ideal conditions for the microorganisms in the sample to grow and multiply. After an incubation period, the colonies of microorganisms are counted to determine the viable count. In contrast, the identification of specific microorganisms follows a slightly different procedure. Here, the sample is subjected to various biochemical and morphological tests. These tests are designed to reveal the unique characteristics of the microorganisms, effectively fingerprinting them and allowing for their identification. And then, after the testing, comes the result analysis. This stage involves interpreting the data collected during the tests. For example, the number of colonies counted in the viable count test gives an indication of the microbial load in the sample. Similarly, the results of the identification tests can reveal the presence of specific harmful microorganisms. However, as straightforward as this might sound, the process is not without its challenges. Contamination is a constant threat that can skew the results. Additionally, some microorganisms are particularly tricky to grow in a lab setting, making their detection and identification a daunting task. But despite these challenges, it's all part of the job for microbiologists. They employ their expertise, coupled with stringent quality control measures, to ensure the reliability of the tests. And so, as complex as the process might seem, it's all in a day's work for a microbiologist. Why bother with all this testing, you might ask? Well, let's delve into the importance and applications of microbial limit tests. Microbial limit tests are crucial for a host of reasons. They play a significant role in the pharmaceutical industry, ensuring that our medications are safe and effective. These tests are used to determine the number of viable microorganisms in a sample and to identify any specific microbes that might be present. The knowledge gained from these tests helps in maintaining the quality of the product, reducing the risk of contamination, and ensuring the safety of the consumer. Imagine if a medicine that is meant to cure ends up causing an infection due to microbial contamination. That's a scenario we all want to avoid, and that's where microbial limit tests come in. They act as a gatekeeper, ensuring that only safe, high-quality pharmaceutical products reach the market. But their role isn't confined to the pharmaceutical industry alone. Microbial limit tests are also extensively used in the food and beverage industry, cosmetic industry, and any other industry where microbial contamination could pose a risk. Moreover, these tests are not just about identifying and counting microbes. They also help in understanding the nature of the microbes, their growth patterns, and how they react to different conditions. This information is invaluable in developing strategies to control microbial growth and prevent contamination. And let's not forget, these tests are a critical part of regulatory compliance. Pharmaceutical companies are required by law to conduct these tests and maintain a certain standard of microbial purity. Failure to adhere to these standards can lead to severe penalties, including fines and product recalls. So, you see, microbial limit tests are not just about ticking off a box on a checklist. They are about safeguarding public health and safety. They are about ensuring that the products we consume are free from harmful microbes. Microbial limit tests are not just a regulatory requirement. They are our first line of defense against potentially harmful microbes. Let's quickly recap what we've learned today. Microbial limit tests, including viable count and specific microorganism identification, are vital tools in the pharmaceutical industry. They allow us to quantify the number of living microorganisms in a sample and identify any specific microbes of interest, respectively. We've delved into the process of these tests, uncovering how they're meticulously carried out to provide accurate and reliable results. Whether it's by counting colonies on a petri dish or using sophisticated techniques like sequencing for identification, these tests are the backbone of microbial quality control. Their importance cannot be overstated. They ensure the safety and quality of our pharmaceutical products, protecting consumers and maintaining industry standards. They're not just about numbers and names, but about safeguarding health and well-being. In essence, microbial limit tests are the unsung heroes of the pharmaceutical world, keeping us safe from unseen threats. Remember, these tests are crucial to ensuring the safety and quality of our pharmaceutical products. Subscribe for more because you won't find me later.